Hi friends, if you are viewing my channel first time, please subscribe to my channel for more updates on embedded systems. Today we are mainly discussing about on some CAN protocol basics. Today's agenda CAN bit timing and also understand how to do the CAN bit timing calculations. Okay, here for example, if I want to communicate between the CAN nodes, we should always use the specific baud rate. Then only all the nodes can communicate effectively in the CAN network. The can communicate up to 1 Mbps. This much speed we can communicate between the CAN nodes. For example, this baud rate depends on the system clock, nothing but external clock frequency. This external clock frequency may vary due to the environmental condition. This leads to an synchronization error. To minimize this synchronization error, the CAN protocol was coming up with this CAN bit timing to do the bit level synchronization between the CAN nodes. So we should always use the CAN bit timing, and we should always follow the same CAN bit timing for all the CAN controllers, so we can communicate effectively. If you are not following any one of the node, if we configure incorrect CAN bit timing, so that may lead to a error frames. So minimize the error frames, so we should always configure the same CAN bit timing. Okay, this CAN bit timing we further divide into the four segment. First one is synchronization segment, second one is propagation segment, and phase buffer segment 1, phase buffer segment 2. And this is nothing but nominal bit timing, nothing but recessive or dominant. We are representing either one of the bit, we are representing into the this four segment. First one is synchronization segment. When we will use to synchronize between the network, between the nodes, we use this segment. Next one is propagation segment. For example, if I want to transmit the data from one node to another node, we need some delay. Okay, to compensate that delay, we are just denoting with the propagation delay. And mainly the distance perspective, we used to have this segment. And next one, phase buffer segment 1 and phase buffer segment 2, we mainly use for the resynchronization purpose. This is the mainly use case of the all four segment. Let us understand more on these segments in the next slide. Okay, first one is here system MCU system clock, nothing but microcontroller system clock or external oscillator. Okay, this is the external frequency we used to give to the microcontroller, and this is the CAN system clock. This frequency is we are giving to the CAN controller. Okay, here system clock, we have one division factor, baud rate prescaler. For example, my system clock is 100 megahertz, my baud rate prescaler is 10. Okay, here we are divide by 10. Okay, 100 megahertz divided by 10, then I will get 10 megahertz. This is nothing but my CAN system clock. Okay, this way we are dividing. Okay, each controller may have different baud rate prescaler. For example, I have given like this. Okay, 100 megahertz, I was dividing with the 10, so I will get 10 megahertz of the CAN system clock. Okay, this way they are dividing the clock frequency. And next furtherly, if I want to specify one time quanta, okay, each time slice I was representing with TQ, time quanta. Okay, one low to high of the CAN system clock, I was mentioning like one time quanta. And how many time quantas we are going to mention in the one nominal bit timing, that we'll see here. For example, I am composing one nominal bit, one recessive or dominant. I was representing with the 8 time quanta, nothing but 8 low to high pulses. Okay, here if you see sync segment, propagation segment, phase segment 1 and phase segment 2, and each nominal bit we divide into the four segment, and in the next bit also we used to denote the same. So if I want to retry how it is sent, right, so we use all the four segment. This is for the synchronization, this is for the transmission delay between the nodes, and this two for the resynchronization purpose. And here the sync segment always only one time quanta, only one low to high, only one time quanta, this is fixed in all the controllers. And this three may vary until 1 to 8. Okay, this propagation segment may represent 1 to 8 time contrast. Similar way, phase segment 1, phase segment 2 also max of 8 time contrast. Okay, that way we used to denote in the one nominal bit. Okay, for example, I wanted to mention with the sampling point. Here we used to mention, for example, here I wanted to detect the exact bit whether it is recessive or dominant. Mainly using this sample point, we are going to decode. Okay, here sampling point at 75 means here 8 time counters. I am dividing into the two divisions. Here see 6 time counters left side and 2 time counters right side. Nothing but 75. 75 I was putting the sample point. Okay, here if you see two time counters nothing but and 25%. Here six time counters nothing but 75. That's why here I was denoting like a 75% of sampling point. Okay, this may vary based on the number of time counters which we defined in the each segment. Okay, that calculation we will understand next slide. And here we will also understand clock synchronization. We have two types of synchronization: hot synchronization and also resynchronization. First, hot synchronization we will understand. Okay, when the hot synchronization will happen, when the receiver recessive to dominant, this always start bit of the each frame, we will have a recessive to dominant transition. Whenever this edge is occurred from the recessive to dominant, at that time we used to restart the nominal bit timing. Then we used to start from here. So this is the kind of hard synchronization. Okay, when the recessive bit to dominant bit transition is occurred, at that time we used to restart the nominal bit timing. Nothing but we used to start from here whenever the transition high to low recessive to dominate. Then we used to start from here, restart from the our nominal bit timing from sync segment. So this is a kind of hot synchronization. Next we'll understand about the resynchronization. For example, this dominant to this recessive to dominant is occurred after the sync segment. For example, this dominant to sorry recessive to dominant, this transition is occurred after the sync segment. So we used to lengthening the this phase segment 1. And similar way, if for example this recessive to dominant, this edge is occurred before the sync segment, then we used to shorten the phase segment 2. This is mainly in the resynchronization purpose, we use mainly phase segment 1 and phase segment 2. And this way we discussed mainly on the synchronization. Mainly bit level synchronization, we use mainly the can bit timing. And this is how we derived time counter. From the number of time counter we were derived the nominal bit timing. Okay, 8 time counters we represented in the nominal bit time. Okay, this is a way we are going to divide our can bit timing. And let us understand some more example with the calculation. Calculate required time counter to achieve 500 kbps baud rate if the system clock is 40 megahertz and clock divider is 4. Okay, this diagram already we seen in earlier. Okay, here in the question they mentioned like 40 megahertz is the system clock and baud rate prescaler is nothing but 4. 40 divided by 4 nothing but can frequency is 10 megahertz. Here if you see can frequency f can nothing but 40 is the system clock divided by baud rate prescaler is 4. Totally I got 10 megahertz of the system clock. Okay, here I will get the time counter and each time counter I will get I got the frequency 1 divided by frequency, I will get the time counter. Okay, here 1 divided by f can nothing but 10 megahertz, I got 100 nanoseconds. 1 divided by 10 megahertz nothing but 100 nanoseconds. This is the one time counter. Then let us calculate the how many time counters there in the one nominal bit timing. Okay, here bit rate we should be aware of. Here this is the baud rate we are going to communicate between the networks. Here 500 kbps as given in the question. And bit timing we get right. This is a bit timing 1 divided by baud rate 2 microseconds. Now we will get number of time counters. This bit timing divided by and time counter is 100 nanoseconds. Then we will get 20 time counters we used to represent in the one nominal bit. This is the way we used to calculate the number of time counters for the each nominal bit. And we'll have another calculation. configure T segment 1 and T segment 2 to set the sampling at 80% of bit time. Okay, here in the earlier example we see 75%. Now I am going to calculate 80% of the bit time. Okay, next here T sig 1 nothing but here dark green, nothing but propagation segment plus phase segment 1 nothing but T sig 1 we used to call, and T sig 2 nothing but phase segment 2. This always we should remember. T sig 1 nothing but probe segment plus phase segment 1. Okay, here if you see the 80% of the bit time equal to here T sync segment plus T sig 1. Here T sig 1 nothing but until here to here divided by total. So the what is the sampling point they have given in the question? 80%. Okay, this is how I was equated T sig 1, that is nothing but T sync segment nothing but this is a 1, always fixed 1, and T sig 1 nothing but propagation segment plus phase segment 1 divided by total T sync segment T sig 1 T sig 2, nothing but complete, that division factor is complete. Okay, if I want to get the 80% of the sampling point, so sync segment plus and sync segment plus here T seg 1 divided by sync segment T seg 1 T seg 2. This is how we got the sampling of 80%. Then let us calculate the T seg 1 and T seg 2. And here already we calculated how many number of time quantas for the complete timing. Here T sync segment plus segment 1 segment 2 total we got 20 time quantas, so I was equated with 20. 1 plus T sig 1, this is the numerator. Here always sync segment is always 1, this is always fixed only in each controller, so I was always 1 plus T sig 1 nothing but probe segment 1 plus phase segment 1. Okay, this one I don't know, that's why here divided by 20 nothing but T segment T sync segment plus T sig 1 T sig 2 nothing but 20, that we replaced this one bit timing, so we got 80%. Okay, if I calculate 16 minus 1 15, totally 15 plus 16, 16 divided by 20 nothing but 80%, that's why we got T sig 1 is 15, T sig 2 is 20 is the total timing, and I was subtracting the sync segment 1 of 1 time quanta, and segment 2 is nothing but sig 1, sorry T sig 1 is 15, totally I got T sig 2 is 4. Okay, if I want to represent with my 80%, so 80%, so I should always mention T sig is 1 time quanta, and T sig 2 nothing but propagation segment, and also phase sig 1 nothing but 15, and last T sig is 2. Okay, in this case if I configure like this, my sample point will be 80%. Okay, and also here we should understand one more sync jump width. Okay, as we already discussed, for example, if the bit transition from recessive to dominant is occurred after that, after the sync segment, so we used to lengthen the segment 1. How much we are going to lengthen based on the synchronization jump width, one of the parameter will be there in the can timing only. Okay, that much we can shift. Okay, synchronize jump width. Okay, one of the parameter will be there. Okay, if it is detecting that transition from high to low, that transition edge triggering. Okay, at that time we used to shift until that as sync jump width, until that much we used to shift to the right. Similar way, if the bit transition is detected from high to low, okay, recessive to dominant is triggered before this one, so we used to shorten this length. Okay, by using SJW, this much length we used to shorten the phase segment 2. Okay, this is how we use the synchronous jump width. This is one of the parameter we use for the to just jump the width from left to right or left to right. Okay, this is how if you want to shift little bit to the left side or right side, mainly synchronization jump width is required. Okay, this is how we used to have this bit timing calculation. That's all, friend. Thank you for watching.